Today, I want to answer a very simple question. How does air-fuel ratio actually affect power output? Not what people recommend, not what's generally considered safe. I mean what the engine actually does on the dyno when we change AFR. So we're going to run a series of controlled tests changing only air-fuel ratio and watch how power moves across the RPM range. Before we start testing, let's get on the same page about air-fuel ratio. AFR is simply the ratio of air to fuel going into the engine. Lower numbers mean more fuel or richer. Higher numbers mean less fuel, leaner. For this test, we are only looking at AFR under load on the dyno, not idle, not cruising, wide open throttle. We're going to start very, very rich at 11:1 air-fuel ratio. We're going to move up to 11.5, 12, 12.5. Finally, we're going to go to 12.75. We're going to end at 13. I really wanted to continue into the leaner area a bit more. I really wanted to use 12.25, maybe even 12.5 if I was able to get there without knocking. I learned during this test that GM designed some engine preservation safety features into their engine computer logic. No matter what numbers you provide in your tuning, the system will not go leaner than 13:1 under wide open throttle. But that's okay, because we still got some excellent data out of it. In this video, we're only changing air-fuel ratio. In an upcoming video, we're going to do the same approach and apply it to ignition timing, one variable at a time, and I will pin that video in the comments once it's live. For now, let's start our AFR testing at the rich end of the scale. Behind me is the result of our 11:1 test. The blue line is horsepower and the red line is torque. Torque is where we're going to be primarily focused in this test. At this point, we don't have anything to compare this to, but it gives us a starting point. You can see where torque begins to rise, where it peaks in the mid-range, and then where it starts to fall off up top. We're not drawing any conclusions yet. This is simply our baseline as we start to lean it out. We're going to do another run now at 11.5 and see how it changes. All right, when we compare the 11 to the 11.5 test, the difference shows up immediately. Here in green is the torque curve from the 11.5 test, and leaning it out just half a point was worth about 3 to 5 pound-feet of torque throughout most of the curve. What's interesting here is that the change is uniform. Even with just this small AFR change, we can already see that different parts of the curve respond differently. Above about 5,700 RPM, we really don't see much difference between 11 and 11.5. So with that comparison in mind, let's go ahead and take the next step and do 12:1. Now we'll compare 11.5 to 12:1. This line in purple is the torque output of the 12:1 test. Just like the previous step, leaning it out another half point doesn't really cost us power anywhere. Again, that small change was worth roughly 3 to 5 pound-feet at different points across the curve. What's also worth noting is that between these two AFRs is about where a stock Z06 like this typically runs from the factory under load. Let's go ahead and take the next step leaner and see what happens at 12.5. Now we're going to compare 12 versus 12.5 AFR. This reddish brown line is our 12.5 torque curve. Leaning it out another half point this time picked up power across the entire RPM range. In most areas, that's worth about 3 pound-feet, and once again, we didn't lose power anywhere. At this point, we're still seeing consistent gains, but as we continue leaning it out, we're going to start moving closer and closer to where things can become more sensitive. Because of that, we're going to make smaller changes, and we're going to go to 12.75 to 1 air-fuel ratio. Now we're comparing the 12.5 and the 12.75 air-fuel ratios. Here in the pink is the 12.75 torque curve. Once again, leaning it out slightly picks up power across almost the entire torque curve. The one exception is right around 5,200 RPM, where the two curves are essentially the same. Everywhere else, 12.75 picked up 3 to 4 pound-feet over the 12.5 AFR. Let's take the final step and see what happens at 13 to 1 air-fuel ratio. Now we're comparing the 12.75 and the 13 to 1 torque curves, and here's where things take an interesting turn. Here in black is the 13 to 1 AFR torque curve. This is the first place where leaning it out further actually costs us power in some areas of the curve. From about 2,700 to 3,400 RPM, we lose about 2 pound-feet of torque with the leaner AFR. At the same time, we do gain about 2 pound-feet right at the peak of the torque curve. This is pretty typical. Engines usually want their leanest AFR where the torque is the highest. So at this point, we are no longer seeing uniform gains. We are starting to see trade-offs, and this is where the conversation changes a bit. Running leaner generally makes more power, up to a point, but it also raises combustion temperature. In the worst cases, running too lean can mean detonation, engine damage, or catastrophic failure. So what we're really looking at here is a trade-off between power and safety. Engines that need every last ounce of torque and horsepower, often with less concern for longevity, are often tuned with a fuel curve that targets the best power AFR at each particular RPM range. For most street-driven engines where reliability matters, a flat AFR often makes more sense. In this case, something like a 12.75 or even a 12.5 AFR gives up relatively little power while maintaining a much wider safety margin. Now let's reset for a moment and compare 11.5, which is around where many factory naturally aspirated engines operate, to 12.75, which is where a lot of tuners ultimately land. Individually, each step that we made was only worth a few pound-feet of torque. So it's easy to dismiss these changes as insignificant. But when we compare a typical starting point, 11.5 in the green, with a typical tuner's endpoint, 12.7 in the pink, the difference becomes more obvious. Across the curve, we've picked up a meaningful torque increase, reaching as much as 8 pound-feet in some areas. Just as important, we've eliminated several torque dips, such as this trough that runs from roughly 2,800 RPM to 3,400 RPM. The result is a smoother, more consistent torque curve, not just a higher one. And this is where the dyno stops telling the full story. As a driver, this kind of change often feels like even more than the numbers suggest. Throttle response improves, the engine revs more cleanly, and the overall operation feels smoother and more eager. Even though the gains look modest, the drivability improvement is very real. So what did we actually learn here? AFR absolutely affects power, but not always in dramatic swings. The changes are incremental, they vary by RPM, and they add up over the entire curve. By comparing factory-style AFR to a more optimized one, we didn't just gain torque, we smoothed the power delivery, eliminated dips, and improved how the engine responds. This is why AFR tuning isn't just about peak numbers, it's about shaping how the engine behaves across its entire operating range. But fuel is only half the equation. In the next video, we're going to do the same type of testing with ignition timing, starting conservative and then continuously advancing timing while watching what the engine actually does on the dyno. Just like in this test, we'll compare each step directly and let the data tell the story. Some of those results may surprise you. If you want to see that test, make sure you're subscribed so that you don't miss it. I'll have the link posted in the comments when it goes live. Thanks for watching, and I'll catch you on the next one.